So, examiners really like to ask differential equation questions in the context of modelling. They're really popular. There's almost one in every exam that they do. So, in this video, I'm just going to go through a bunch of past exam questions. This video isn't necessarily focused on solving differential equations, as the last video I uploaded is completely dedicated to that. I'll go through it briefly in this video, but I recommend going back to that video. It's called Solving Differential Equations, if you need a reminder of that. But here's an example question to start off with differential equations in modelling. Okay, so for this question, we're told about this differential equation here, where dh over dt is equal to h cos of 0.25t over 40. And this differential equation models a passenger on a roller coaster, where h is the height above the ground of the passenger, and this is in meters, and t is the time from the start of the ride, and this is in seconds. And we're told that given that the passenger is 5 meters above the ground at the start of the ride, we need to show that h is equal to this here. So we need to solve this differential equation. Now, as I talked about in the last video, there are 3 steps to solving a differential equation. Firstly, we have to rearrange the differential equation to get all the y terms onto one side of the equation and all of the x terms onto the other side of the equation. Now, here we don't have y and x. We have the h, which is the y, and the t, which is the x. So we need to get all the h terms onto one side of the equation and all of the t terms onto the other side of the equation. And then secondly, we need to integrate both sides of the equation. And then thirdly, after we've done that, only if the question asks, we need to make y, or in this case h, the subject. And as part A wants us to show that h is equal to this here, it wants us to make h the subject. So therefore we need to do this third step as well, because it's asking us to make h the subject. Okay, so let's solve this differential equation. So firstly, we need to rearrange this in order to get all the h terms onto one side and all of the t terms onto the other side. So let's start with this h here, and we want to bring this onto this side with the dh. So what we're going to do is we're going to divide both sides by h. So on this side it cancels out, and then on the other side it's going to be 1 over h, and then this dh over dt. And then what we want to do is, because we've got all the h terms onto this side now we want to get this dt term onto this side. So what we're going to do is we're going to multiply both sides by dt. So on this side it goes away, and then it becomes 1 over h dh is equal to 1 over 40 cos of 0.25t dt. So we've done the first step because we've got all the h terms on this side and all of the t terms on this side. Okay, and then for the second step, we need to integrate both sides of this equation here. So if we do this, it will look like this, where on this side it's the integral of 1 over h dh, and then on this side it's the integral of 1 over 40 cos of 0.25t dt. I've taken the 1 over 40 out of the integral, so we'll just focus on integrating this cos of 0.25t. So if we start with this side here, this is the format that we've seen loads of times in year 2 integration, the 1 over x, and when we integrate this, this is the natural log of the modulus of x. So when we integrate this, it's going to be the natural log of h. We don't need to worry about the modulus symbols here, because we're told that h is the height above the ground of the passenger, and we can assume that the passenger isn't going to go below ground, so we can assume that h is never going to be a negative number, so we don't need to worry about the modulus signs here. And then on this side, we need to integrate the cos of 0.25t. Now, we talked about how to integrate functions like this in the integrating f ax plus b video, so go back to that if you need a reminder. But we need to integrate cos here, and when you integrate cos, it's sin, so it's going to be sin of 0.25t. But remember, you also need to divide by the coefficient of t, which is this 0.25. So it's going to be 1 over 0.25, and this is equal to 4. So therefore it's going to be 4 sin of 0.25t when you integrate this here. Remember the 1 over 40 at the start, and then also remember the plus c on the end, and then 1 over 40 multiplied by 4 is 1 over 10. So we're left with this equation here. So now we need to do this third step here. So at the moment on this side, it's the natural log of h, and we need to show that it's h on this side and show that it can be written like this here. And the easiest way to do this is if you remember your laws of logs. For both sides of this equation, we can make them a power to base e like this here. And what's good about this is, remember, when you have e to the power of the natural log of something, these two just cancel out and leave you with h like this here. And then we can also simplify this side here if you remember your laws of indices. So we have this term plus c, and remember, when you have two things that are inside a power that are adding together, you can split them up into two different powers by multiplying them together. So we can write this here as e to the power of this term multiplied by e to the power of c, so we can separate it like this. And then if we say something like a is equal to e to the power of c, because remember that c is a constant, so therefore e to the power of c will also be a constant. So if we say that a is equal to this, we can write this as h is equal to a e to the power of 1 over 10 sin of 0.25t. Okay, so we've got this equation here, and this is what they've got in part A, but instead of this A here, they've got this 5. And the reason that they can figure this out is because of this last sentence here, that the passenger is 5 meters above the ground at the start of the ride. So t is the time in seconds from the start of the ride, and as the passenger is 5 meters above the ground at the start of the ride, this is where t is equal to 0. And as h is the height above the ground of the passenger in meters, and it's 5 meters above the ground, therefore here h is equal to 5. So what this sentence is saying is h is equal to 5 when t is equal to 0. And we can use this information here to sub in the values of h and t and find the identity of a. We talked about stuff like this in the last video about the general solution and the particular solution when we sub in these values. So if we sub in h is equal to 5 and t is equal to 0 like this here, so all of this here will simplify down to 0, so it's going to be e to the power of 0. Remember, e to the power of 0 is 1, so this is going to be that 5 is equal to a. So this is the value of a, so therefore we can write this equation here as h is equal to 5e to the power of, they've written it here as 0.1 instead of 1 over 10 of sin of 0.25t. So we found the value of a here as 5. Okay, so for part B, we need to find the maximum value of the passenger above the ground. And this is kind of related to Year 2, Chapter 7 content, where we were talking about trigonometric modelling. So we need to find the maximum height of the passenger above the ground. So we need to find the maximum value of h. So therefore, we need to find the maximum value of this term here. And this term will be at its biggest when the sin part is at its maximum. And we talked about this during Year 2 of Chapter 7 in trigonometric modelling. It doesn't matter what is inside this bracket here. The maximum value of sin is always 1. If you look at a sin graph, the biggest value that it can have, its maximum, is at 1. So therefore, for this value here, again, it doesn't matter about what's inside the bracket here. For this value here, we're just going to sub in 1 because this is the maximum. And therefore, this is going to be 5e to the power of 0.1. This is going to be equal to h. And then if you put this into a calculator, it's equal to 5.53. So the maximum height of the passenger above the ground is when sin is 1, and this is 5.53 meters. Okay, so for part C, we're told that the passenger reaches the maximum height for the second time, t seconds after the start of the ride, and we need to find the value of t. So as we talked about in part B, this maximum height is reached when sin is its maximum, which is 1, so therefore sin is this here, so therefore this maximum height is going to be reached when sin of 0.25t is equal to this maximum, so 1. So we have this equation here. Now, what's important about this question is it says it wants us to find the time where it reaches the maximum height for the second time. So if we look at this graph here, we're not looking for this value because this is the first time, we're looking for this value, so the second time. So if we look at this equation here, we can take the inverse trig function and say that 0.25t is equal to arcsin of 1. And if you figure this out using your calculator, or you look at this graph here, you can see the arcsin of 1 is at pi over 2, and then 5 pi over 2, and then it will continue like this, 9 pi over 2, and then it will continue so on. And we're looking for the second time, so we're not looking for this pi over 2 here because this is the first time. We're looking for when 0.25t is equal to 5 pi over 2, and then we can divide both sides by 0.25 to get that t is equal to 10 pi, which if you put into your calculator is equal to 31.4. It would be 31.4 seconds because it's t, so it's in seconds. So this is the time for when it reaches its maximum height for the second time. Okay, so here's another question on differential equations in the context of modelling. Okay, so for part A, we need to express 1 over p 11 minus 2p in partial fractions. Now, we did a video on partial fractions back in year 2 of chapter 1, so go back to that if you need a reminder of how they work. But we're going to split this up into two partial fractions. One of them is going to have this denominator of p, and the other one is going to have this denominator of 11 minus 2p. And we're going to call the numerators a and b, and we need to find what these are. Okay, so what we're going to do is firstly this equation here, we're going to multiply all the terms in this equation by this denominator, so this p 11 minus 2p. So if we start with this term, this will just cancel out the denominator and leave us with the numerator, which is 1. And then if we focus on this term here, this p denominator will cancel out with this p that we're multiplying by to just leave us with a multiplied by 11 minus 2p. And then if we focus on this term here, this 11 minus 2p denominator is going to cancel out with this 11 minus 2p bracket and just leave us with b multiplied by p. So we're left with this equation here. So what we're going to do with this equation, you can do two methods. You can either do substitution or you can equate the coefficients. I'm going to do substitution because I think it's the way that most people prefer and it's the easiest in my opinion. So what we're going to do is we're going to make substitutions for p to make this and this equal to 0 and then rearrange in order to find a and b. So if we start with this here, this bp, if we just let p equal 0, this term here is going to cancel out, it's going to be equal to 0, and we're just going to be left with 1 is equal to a, and then we sub in p is equal to 0 here, so this will cancel out and just leave us with 11, so it's going to be 11a like this here, and then divide both sides by 11, so we get that a is equal to 1 over 11. And now we need to find b, so what we need to do is make a substitution to make this bracket here 11 minus 2p equal to 0. So if we move the minus 2p onto the other side, so we get 11 is equal to 2p, and then divide both sides by 2, so we get that 11 over 2 is equal to p. So if we let p equal 11 over 2, this bracket here is going to be equal to 0. So therefore this whole term is going to cancel out and be 0, so we're just going to be left with 1 is equal to, and then if we sub in p here, it's going to be 11 over 2b, and then divide both sides by this 11 over 2 to get that b is equal to 2 over 11. So therefore we found the identities of a and b, so therefore we can write this as these partial fractions 1 over 11 over p plus 2 over 11 over 11 minus 2p. What we can do as well to make it a bit simpler, because we kind of have these awkward fractions inside a fraction, we can move these denominators here into this denominator. So it will become 1 over 11p plus 2 over 11 and then multiplied by 11 minus 2p like this here. Okay, so for part B, we're told about this differential equation here that dp over dt is equal to 1 over 22 p 11 minus 2p, and we're told that this differential equation models a population of meerkats, where P is the population of meerkats in thousands and T is the time measured in years since the study of the population began. And we're told that given that there were 1,000 meerkats in the population when the study began, we need to determine the time taken in years for this population of meerkats to double. Okay, so to start with, let's actually break down what this part B is actually asking us, okay? So here we're told that given that there were 1,000 meerkats in the population when the study began, so there were 1,000 meerkats in the population, so P is the population of meerkats, but remember it's in thousands. So therefore here, if there are 1,000 meerkats, P is equal to 1, because remember it's in thousands. And we're told this is when the study began, and as T is the time measured in years since the study began, therefore here, as is at the start, T is equal to 0. So that is what this sentence here is saying, that P is equal to 1 when T is equal to 0. And then we're told that determine the time taken in years for this population of meerkats to double. So we need to double 1,000, so it's going to be 2,000. So P is going to be equal to 2. And we need to determine the time taken in years for this to happen, for this population to double. So therefore, we need to find what T is. So that is what the question is actually asking us. Find T when P is equal to 2. Okay, so to do this, we're going to have to solve this differential equation up here. So remember the steps for solving a differential equation. Firstly, we need to rearrange it to get all the P terms onto one side and all of the T terms onto the other side. So if we start with this P11 minus 2P and we move this onto this side, so we're going to divide both sides by P11 minus 2P. So it's going to be 1 over P11 minus 2P. dP over dt is equal to 1 over 22. And then we're going to move this dt onto this side, so we're going to multiply both sides by dt, so we get that 1 over P11 minus 2P dP is equal to 1 over 22 dt. And we can do some more simplifying here, because in part A we showed that this 1 over P11 minus 2P can be split up into these two partial fractions, so we can write it like this here. Now we've got this 1 over 22 and we've got this 11 in the denominator here and this 11 in the denominator here as well. So to simplify this equation, we're going to multiply all the terms by 22. So here this will cancel out and just leave us with 1. This 11 will cancel out here and it will be 2 times 2 in the numerator, so it will be 4 because we're multiplying by 22. And then here this 11 will cancel out and it will also multiply by 2 here because we're multiplying by 22. So overall we're going to be left with this equation up here, okay, and this is in a simpler format. So now we need to do the second step, so we need to integrate both sides of this equation. Okay, so we have to integrate this equation here. So let's start with this side, and we have two terms, so let's consider them individually. So if we start with this 2 over p, I've taken the 2 out of the integral, so it's the integral of 1 over p. This is of the form that we've seen already, this 1 over x, so it's going to be equal to the natural log of p, and then we've got this 2 at the front. We don't need to worry about the modulus signs around the p, because p is population and a population can't be negative, so therefore p can't be negative. And then if we focus on this 4 over 11 minus 2p, I've taken the 4 out of the integral like this here, so we're focusing on this integral. This we also talked about in the integrating f ax plus b video. So this integral here is actually also of the form 1 over x. Instead of the x here in the denominator, we've got this 11 minus 2p. So when we integrate this, it's also going to be the natural log, but instead of being the natural log of x, it's instead going to be the natural log of 11 minus 2p. But remember, we also need to divide by the coefficient of x, or in this case the coefficient of p, which is minus 2. So if you divide by minus 2, it's minus a half. And then this 4 here that we took out at the start, multiplied by by this minus a half is equal to minus 2. Just quickly as well, with this 11 minus 2p, we don't need to worry about putting modulus signs around this either, because we're told in the question that p is bigger than 0, but it's also less than 5.5. If you sub 5.5 into this 11 minus 2p is equal to 0. Now, if p started to be bigger than 5.5, we would have an issue, because then 11 minus 2p would start to be negative, and then we would have to put these modulus signs around the 11 minus 2p. But as p can't be bigger than 5.5, it's less than 5.5, in this interval here, 11 minus 2p cannot be negative, so we don't need to worry about the modulus signs. Okay, so therefore if we add these terms together, it's going to be 2 natural log of p minus 2 natural log of 11 minus 2p. And then if we focus on this side here, the integral of 1 dt, remember when you integrate a constant like 1, it's just equal to t, like this here. And then remember the plus c on the end. Okay, so we've done the integration and we're left with this equation here, and now we need to find the plus c, and we can do this because of this sentence that p is equal to 1 when t is equal to 0. So what we can do is sub in this value of p and t and then rearrange to find c. So this is what I've done here. I've subbed in p is equal to 1 and t is equal to 0 into this equation, and we can do some simplifying because the natural log of 1 is 0, so this term will go away, and then 11 minus 2 multiplied by 1 is 9, so this is going to be minus 2 natural log of 9, and then on this side it's just going to be c. So therefore c is equal to minus 2 natural log of 9. So we can sub this into the equation to get this here, which is the full equation. And now what we need to do is this here. So we know that p is equal to 2, but we want to find t, so sub in p is equal to 2 and rearrange to make t the subject. So that's what I've done here. I've subbed in p is equal to 2, and we can do some simplifying here. We've got this 11 minus 2 times 2, which is going to be 7, so it's going to be minus 2 natural log of 7, like this here. 2 natural log of 2 minus 2 natural log of 7. Remember your laws of logs, that this will divide the natural log, so it's going to be 2 divided by 7, so it's going to be 2 natural log of 2 over 7, and then we can move this minus 2 natural log of 9 onto this side like this here, and then we've got these two logs that are added together, so they'll multiply, so it's going to be 2 multiplied by 9, so it's going to be 18 over 7 like this here. So t is equal to 2 natural log 18 over 7. It wants us to determine the time taken in years, so let's convert this into a decimal. If you put it into your calculator, it's equal to 1.89. So the time taken in years is 1.89 years. Okay, and then for part C, we need to show that this equation here can be rearranged into this form here, where p is equal to this function. So we need to make p the subject. This is essentially the third step for solving a differential equation, like we talked about before, where we need to make y, or in this case p, the subject. Okay, so let's start with this side here of the equation. So we have these two logs that are minusing, so this natural log minus this natural log. So remember the laws of logs, we can divide the terms inside the log, so it becomes p over 11 minus 2p, and we can also do this with this log here. So if we bring this onto the other side, so it's plus 2 natural log of 9, and then we've got this natural log plus this natural log, so this 9 will go in the numerator because they're multiplying together, so it'll be 9p over 11 minus 2p. We can do this because the coefficients of all these logs are the same, they're all 2. Okay, so what we're going to do now is we divide both sides by 2 to get rid of this coefficient here, so it becomes the natural log of this is equal to half t. And now what we're going to do is, to both sides of the equation, we're going to make them powers to base e, like this here. So if we do it on this side, it's going to become e to the power of half t. And if we do it on this side, let's just call this function here, let's call this x. So it'll become e to the power of the natural log of x. And remember the laws of logs, when you have e to the power of the natural log of x, this e and natural log essentially cancel out and just leave us with x. So therefore this side will just become 9p over 11 minus 2p. So that's why we do this step here, to get rid of this natural log. So we're left with this equation here. Now this fraction on this side is kind of annoying because we have two terms in the denominator and one term in the numerator. We would prefer that to be the other way round. So what we're going to do for both sides of this equation, we're going to do 1 divided by the terms. So 1 divided by this term and 1 divided by this term. So therefore on this side the fraction will flip. So it's now going to be 11 minus 2p over 9p. And then on this side, it's going to be 1 over e to the power of half t. And remember your laws of indices, this will be equal to e to the power of minus a half t. So we can write it like this here. And what's useful about this is we can now divide this more easily. We can work with this fraction more easily when we've got more terms in the numerator than the denominator. So firstly, let's move this 9 onto this side. So multiply both sides by 9. So now it would be 9e to the power of minus half t, like this here. And these two terms in the numerator and this one term in the denominator, we can individually divide these terms in the numerator by the denominator. So this will be 11 divided by p, so it'll be 11 over p, and this will be minus 2p divided by p, so this p's will cancel out, just leave us with minus 2. So we've got it in this format here, and then this minus 2 we can move on to the other side, so it becomes 2 plus 9e to the power of minus half t, and we've got this p in the denominator now, so we kind of want it in the numerator to make p the subject. So we're going to do the same thing as we did here. We're going to do 1 divided by both sides. So on this side the fraction will flip, so it's p over 11, and then on this side it will be 1 divided by 2 plus 9e to the power of minus a half t, and then multiply both sides by 11 to get rid of this denominator. So we get that p is equal to 11 over 2 plus 9e to the power of minus a half t, and this here is the final answer that is in this form here. I'll be honest, I think this is a pretty difficult kind of rearranging question. Hopefully if you go for it slowly enough it makes sense. Okay, so here's another past paper question on differential equations in the context of modelling. Okay, so this is a really wordy question that talks about a model for the radius of a mint. So we're told that a spherical mint of radius 5mm is placed into the mouth and sucked, and 4 minutes later the radius of the mint is 3mm. And we're told that in a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius, and we need to use this information to find an equation linking the radius of the mint and the time. And we need to define the variables that we use, because it hasn't actually given us any variables here. It hasn't given us any letters like y or x. It's just a very wordy question. Now I would really recommend going back to a video that we made in year 2 differentiation titled Rates of Change and Differential Equations, because we talk about questions like this and how to break them down when they're very wordy and what the question is actually trying to ask us in terms of maths. So I'd really recommend going back to that video and try and recap it here as best as I can. So firstly, it says that we need to define the variables that we use because they haven't given us any. So let's actually look at what the question is asking us. It wants us to find an equation linking the radius of the mint and the time. So there's two variables here, the radius of the mint and the time. So the radius of the mint, let's say that this is r, and the time, let's say that this is t. So what part A is asking us is to find an equation linking r and t. Okay, so we've slightly simplified it. Okay, now this part up here, we're going to ignore this for now because this comes later. I want to first focus on this sentence here because this is really important. It tells us that in a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. Now we talk about it in the video that I referenced. This is a really important sentence, and the key word here is rate. And we talked about in that video that whenever you see the word rate, it's equal to d something over dt. So rate, whenever you see this word, is equal to d something, so whatever it's talking about in regards to rate, over dt, where t is time. That is what the rate is talking about. And it says that it's talking about the rate of decrease of the radius of the mint. And we established that the radius of the mint is r, so it's the rate of decrease of r, so therefore this value here is going to be r. So this sentence up here is dr over dt. This is what it's saying. Okay, so this is really important. You need to extract this information, and we're told that it's inversely proportional, so we need to use the proportional sign here, that dr over dt, this rate, is proportional. Okay, so let's break down what's going on. So this is inversely proportional. So remember, inversely proportional means it's 1 over and then whatever it's talking about in this regard. That's what inversely proportional means. And we're told it's inversely proportional to the square of the radius. So the radius is r, and it's inversely proportional to the square of the radius. So it's r squared. So therefore it's 1 over r squared. So dr over dt is proportional to 1 over r squared. But there's one other key detail, is we're told it's a rate of decrease. Now if it's a rate of increase, it's going to be positive, but in this case it's a rate of decrease, so it's going to be negative. So therefore dr over dt is proportional to minus 1 over r squared. And this here is the important information that we need to extract from this sentence here. And we can go further with this, because this proportionality sign here, we talked about it in the video. This proportionality sign, we can replace this with an equal sign and with a constant k. So therefore, if we replace this proportionality sign, it would be dr over dt is equal to k multiplied by minus 1 over r squared, where k is a constant that we need to find. And we can move this k into the numerator here, and we can establish that dr over dt is equal to minus k over r squared. And this here is the differential equation that we're going to be using in this question. And we've got all that from kind of extracting the information from this quite wordy question. So as I said, go back to that video titled Rates of Change and Differential Equations, where we talk further and give more examples of questions like this. But we've extracted this differential equation here that we need to work with. Okay, so now what we need to do is actually solve this differential equation here to get an equation linking r and t. Okay, so remember the steps for solving a differential equation. Firstly, we need to get all the r terms onto one side of the equation and all the t terms onto the other side. So we have this dr over dt, so let's get the r terms onto this side. So over here we have this k over r squared. So what we're going to do with this equation is we're going to multiply all the terms by r squared to cancel out this denominator here, and then on this side it's going to become r squared dr over dt, and this is equal to minus k. And then we're going to get this dt onto this side of the equation by multiplying both sides by dt. So we get that r squared dr is equal to minus k dt. And then remember, the second step for solving a differential equation is we need to integrate both sides of this equation. So this is actually quite easy. This is just year one integration. So if we start with this r squared, if we integrate this, this is equal to 1 over 3 r cubed. And then if we integrate this minus k, remember k is just a constant, so therefore if we integrate this minus k, it's just going to be minus kt, and then remember the plus c on the end. Okay, so we're left with this equation up here, and now what we need to do in order to get a full equation is to find the identities of k and C. And we can do this because of the information that we're given at the start. And in these two short sentences, we're actually given a lot of information that we need to extract. So let's start with this first sentence. So we're told a spherical mint of radius 5 mm is placed into the mouth and sucked. Okay, so let's put this into context with our variables R and T. So we're told that a spherical mint of radius 5 mm, so that means that R is equal to 5, and we're told that this mint of radius 5 mm is placed into the mouth and sucked. Now this part here is when it starts to actually decrease in radius, kind of when the mint is being sucked away. But what this sentence is saying is at the start, when this mint is first placed into the mouth, its initial radius is 5 mm. So that means that R is equal to 5 when T is equal to 0. This is at the start where the mint is just placed into the mouth. Okay, so we have this point here, and if we look at this second sentence, so 4 minutes later, the radius of the mint is 3 mm. So R is equal to 3 because it's 3 mm in radius, and it's 4 minutes later after it has just been placed into the mouth. If we assume that T is in minutes, we can say that T is equal to 4 here because it's 4 minutes later after this. So R is equal to 3 when T is equal to 4. So we've got 2 points here, and we can use these points and sub them into this equation in order to find the values of the constants K and C. Okay, so let's do this. So let's start with this R is equal to 5, T is equal to 0. So we're going to sub in R is equal to 5, T is equal to 0, like this here, into this equation. So 1 over 3, 5 cubed is equal to 125 over 3. And this minus KT, if we sub in T is equal to 0, this term will just go away. So it will just leave us with C on this side. So that means that C is equal to 125 over 3. So we can sub this in, and this equation becomes this here, where we found the identity of C. And now what we can do is plug in this point here. R is equal to 3, T is equal to 4. So let's sub in these points here. So R is equal to 3, T is equal to 4. So we can simplify this because 1 over 3, 3 cubed is equal to 9, minus K times 4 is going to be minus 4K, and then we've got this 125 over 3 here. We can move this onto the other side, so it becomes minus 4K is equal to minus 98 over 3 if you put it into your calculator, and then divide both sides by minus 4 to get that K is equal to 49 over 6. So we can sub in K now, and we've got this full equation here, that 1 over 3 R cubed is equal to minus 49 over 6T plus 125 over 3. Now we've got some fractions in this equation, and we can get rid of these kind of denominators here because they're a bit nasty. So what we can do is multiply this whole equation through by 6. So here this 49, this denominator will go away. On this side, this 3 denominator will go away and leave us with 1 times 2, which will be 2R cubed. And then this 125 over 3, this denominator will go away and leave us with 125 times 2, which is 250. So overall, we've got this equation here that links the radius of the mint R and the time T, which is 2R cubed is equal to minus 49T plus 250. Okay, and then for part B, we need to find the total time taken for the mint to completely dissolve, and we need to give our answer in minutes and seconds to the nearest second. Okay, so we need to use the equation that we found in part A, and for the mint to completely dissolve and go away, R needs to be equal to 0. We need to find the total time taken for this to happen, so we need to find what T is. Okay, so what we're going to do is sub R is equal to 0 into this equation and then rearrange in order to find T. So that's what I've done here, and this side here will just be 0. So we've got that 0 is equal to minus 49T plus 250. Move the minus 49T onto the other side to get the 49T is equal to 250, and then divide both sides by 49 to get that T is equal to 250 over 49. And if you convert this into a decimal, you get that it's 5.102 minutes. Now, we can't give the final answer as this to get all the marks because it wants us to give our answer in minutes and seconds. So this isn't in minutes and seconds, this 5.102 minutes. So how many seconds does this mean? Okay, it's 5 minutes because we've got this 5 here, but we've got this 0.102 minutes. Okay, so how do we convert this into seconds? Okay, well, there are 60 seconds in a minute. So therefore, what we can do with this 0.102, we can multiply this by 60 in order to find out how many seconds this is equivalent to, which is 6.12. So that means that it takes 6.12 seconds, this 0.102. So therefore, this 5.102 minutes is going to be 5 minutes and 6 seconds if we round it to the nearest second as it asks us to. So the time taken for this mint to completely dissolve is 5 minutes and 6 seconds. Okay, and then for part C, we need to suggest a limitation of the model. Now, I've just put up the mark scheme here because there's loads of answers that you could give for a question like this, and this isn't a finite list, these are just examples. There are other answers that you could give that they would accept. They're normally quite lenient with questions like this. As long as you give kind of a remotely sensible suggestion, they will most likely give you the mark. Of the answers that they've listed here, I think the ones that I would give, I think the module does not consider whether the mint is bitten. I think that's quite good. I think also that the model indicates that the radius of the mint is negative after it dissolves. I think it's quite a good one. We showed in part B that 5 minutes and 6 seconds is how long it takes for the mint to completely dissolve. If you use t values bigger than this, so for example, if you sub in t is equal to 6 or 7, the radius starts to become negative, which obviously doesn't make any sense. The radius can't be negative, so that's a bit of an issue with the model. I think also the model doesn't consider the temperature of the mouth as well. There's kind of loads of answers. If you kind of just give any sensible suggestion, they will most likely give you the mark. Okay, so here's another exam question involving differential equations in modelling. Okay, so in this question, we're told a large spherical balloon is deflating, and this balloon being a sphere is actually important, as we'll talk about in a sec. And we're told at time t seconds, the balloon has radius r centimeters and volume v centimeters cubed. And what this sentence is doing is just establishing the variables. It's not like before where we had to design them ourselves. We're told here that t is time, r is radius, and v is volume. And we're told that the volume of the balloon is modelled as decreasing at a constant rate. And we have this key word here, rate. And we need to use this model to show that dr over dt is equal to minus k over r squared, where k is a positive constant. Okay, so this is another type of question that we talked about in that year 2 differentiation video that I've already referenced, that was titled Rates of Change and Differential Equations, but I'll explain it here as well. So let's go through this slowly. So let's start with this sentence here, and as I said before, we have this key word here, rate. Remember, whenever you see rate, you need to be thinking d something over dt. And what this question is talking about, or this sentence, is the volume of the balloon, which is v, is modelled as decreasing at a constant rate. So therefore, this here is going to be v. So this sentence is talking about dv over dt, okay? And we're told that the volume is decreasing at a constant rate. So as it's constant, this means that dv over dt is going to be equal to a constant. We don't know what this constant is, so at the moment we're just going to call it a, but it's going to be equal to a constant. But we're also told it's decreasing, so it's going to be negative. So therefore dv over dt is equal to minus a here. So we've established this. However, this is not what the question is asking us. It's asking us to find dr over dt. So how do we find this? Well, we can find this by using the thing that I talked about before, that this balloon is a sphere. And this is useful to us because we know the volume of a sphere. We know that the volume of a sphere is equal to 4 over 3 pi r cubed, where v is the volume and r is the radius. And with this equation here, we can differentiate this in terms of r to get dv over dr. So if we differentiate this here, this 4 over 3 pi will still be here, and then it's going to be multiplied by, and then we're going to differentiate r cubed. This is just year 1 differentiation. This is 3 r squared. And then this 3 will cancel out with this 3 denominator to leave us with 4 pi r squared. So dv over dr is equal to 4 pi r squared. Okay, so unfortunately for part A, this is not what we want either. We want this dr over dt. However, what we have done here is we've created two differential equations, this dv over dt and dv over dr. And we talked about this in the video that I referenced. We can multiply these two differential equations together in order to get dr over dt. And what's quite nice about multiplying differential equations together is they sort of work like fractions. So what do I mean by this? So we want dr over dt, okay? So in order to get this, we're going to want dr in the numerator and dt in the denominator. And the other two terms here, we want these to cancel out. And you can see that in both of these differential equations, we have dv present that we don't want in the final answer, this dr over dt. So therefore we can make them, these two terms here, and then if we multiply these dv's will cancel out and just leave us with dr over dt. This is quite nice about differential equation, they kind of work like fractions when you multiply them together. So therefore we're going to multiply these two differential equations together, okay? So we have dv over dt, this is this minus a, however we don't have dr over dv, we have dv over dr. However, what's also nice about differential equations in terms of how they work like fractions is dr over dv is equal to 1 divided by dv over dr. It also works like fractions, where when you do 1 divided by a fraction, it flips the denominator and the numerator. So this is how we can find this dr over dv. So it's going to be 1 divided by this dv over dr, so 1 divided by 4 pi r squared. So therefore this is going to be equal to 1 over 4 pi r squared, like this here. So therefore dr over dt is going to be equal to dr over dv, which is 1 over 4 pi r squared, multiplied by dv over dt, which is minus a, okay? And we can bring this minus a into the numerator to get this a over 4 pi r squared, and then we can put this minus here, like this. Now, in the final answer for part A, it wants us to show that this dr over dt is equal to minus k over r squared, where k is a constant. So what we're going to do, this a and this 4 pi in the denominator, we're going to take this out with a fraction, so it becomes dr over dt is equal to a over 4 pi times minus 1 over r squared, okay? And this minus 1 over r squared, you can see is that we want this in the final answer. And this a over 4 pi is a constant, because a is a constant, as we said, and 4 pi is a constant. So what we can do is we can say that k is equal to a over 4 pi, this is a constant, and we can sub this in to get that dr over dt is equal to minus k over r squared. We've kind of moved this k here back into the numerator, and therefore we have shown that this part A is true. Okay, so for part B, we're given 3 bullet points here. We're told that the initial radius of the balloon is 40 centimeters. After 5 seconds, the radius of the balloon is 20 centimeters. And we're also told that the volume of the balloon continues to decrease at a constant rate until the balloon is empty. And given all that information, we need to solve the differential equation to find a complete equation linking r and t. So I'm going to ignore this for now, this information. We're going to use this later. What I'm first going to focus on is this equation that we found in part A, and we need to solve this differential equation. Okay, so we're going to go through these steps for solving a differential equation. So firstly, we need to get all the r terms onto one side of the equation and all the t terms onto the other side. So we have the dr in the numerator here, so let's move this r squared onto this side. So let's multiply both sides by r squared to get rid of this denominator, so it become r squared dr over dt is equal to minus k, and then move this dt onto this side to get r squared dr is equal to minus k dt. And then remember the second step, we need to integrate both sides of this equation, and this is quite easy. This is just year 1 integration. When you integrate r squared is equal to 1 over 3 r cubed, and as k is a constant, when you integrate this minus k dt is going to be minus kt, and then remember the plus c on the end. So now we're going to use this information here in order to find the values of k and c, these constants here. So So let's start with this. The initial radius of the balloon is 40 centimeters, so r is in centimeters. So that means here r is equal to 40, and we're told that this is the initial radius, so this is where t is equal to 0. And then if we look at this second bullet point here, we're told that the radius is 20 centimeters, so r is equal to 20, and it's after 5 seconds, so t is equal to 5. So we have 2 points here that we can sub into this equation in order to find k and c. So let's start with the r is equal to 40, t is equal to 0. Let's sub these in like this here. So 1 over 3 40 cubed is equal to 64,000 over 3. And then this minus k times 0 will just cancel out and just leave us with c. So c is equal to this 64,000 over 3. So we can sub this into this equation like this, and now we can use this point here, r is equal to 20, t is equal to 5. We can sub this in. So on this side we've got this 1 over 3 20 cubed, which is going to be 8,000 over 3. This will be minus 5k, and then we've got the plus 64,000 over 3. We can move this onto this side to get minus 56,000 over 3 is equal to minus 5k, and then divide both sides by minus 5 to get the k is equal to 11,200 over 3. And we can sub this in to get this equation here. Now we have these fractions as the coefficients, so what we can do is just multiply everything through here by 3 to cancel out all these denominators to get this final equation here. The r cubed is equal to minus 11,200t plus 64,000. You could leave it in this form here, but it's a bit simpler if you get rid of these denominators. Okay, and then for part C, we need to find the limitation on the values of t for which the equation in part B is valid. So this is the equation in part B that we figured out. And what this question is asking is the values of t. What values of t can you sub in for this equation to make sense? And then at what point do you start subbing in values for t and the equation starts to fall apart and doesn't make any sense? Okay, so probably the best way to assess this is as this equation is modelling a balloon deflating. Let's see what this equation predicts the time is going to be when this balloon completely deflates. So this is going to be where the radius is equal to 0 because the balloon will completely deflate. So let's sub this in for r. So it's going to be 0 is equal to this side here like this, and we're going to solve for t. So if we move this minus 11,200t onto this side, we get this, then divide both sides by this 11,200 to get that t is equal to 40 over 7, or if you put this into decimals, 5.71 seconds. Okay, so 5.71 seconds according to this model is when the balloon completely deflates. Now the problem with this is if we start to go beyond this value of t, if we start to go like 6, 7, 8 seconds, stuff like that, the equation no longer makes any sense because the balloon has completely deflated, and it will start giving back negative values of r, which obviously doesn't make any sense. R can't be negative, it's the radius of the balloon, you can't have a negative radius. So therefore the answer to this question, the limit on the values of t for which the equation is valid, is only when t is less than this 40 over 7 or equal to it. Those are the only values in which it's correctly modelling the balloon deflating. Once you go beyond that, once you get higher than this value, r will start to become negative. Okay, so here's another exam question involving differential equations and modelling. This is a really long question, it's really difficult for me to get it on the screen, so I've kind of cut it in two. So the question starts here and then it goes down like this, and then it keeps going down like this here. It's hard to read any of it because it's too small. When I go through the individual sections, I'll enlarge them. Okay, so in this question, we're given this figure here, and we're told that water flows at a constant rate into a large tank. So this is the tank here, and this darker portion is the water inside the tank. And we're told that the tank is a cuboid, which we can see from the diagram. And we're told that the base of the tank measures 8 by 3 and the height of the tank is 5, and we can see this information in the figure. And we're told that there is a tap at a point T at the bottom of the tank. So this is this point here, T, and this is a tap, and when this tap is opened, water can leave the tank through this tap, okay? And we're told that at time t minutes after the tap has been opened, so this means that water can leave the tank, we're told firstly that the depth of water in the tank is h meters, and we can see this on the diagram. And we're also told that water is flowing into the tank at a constant rate of 0.48 meters cubed per minute. And we're also told that water is modelled as leaving the tank through the tap, so this tap here, at a rate of 0.1 h meters cubed per minute. And we need to show that this differential equation here is true, involving dH over dt. Okay, so we're given a lot of text here about the question, but a lot of it we don't need because it's given to us in the figure, a lot of this information. However, there is some important information in this text, and I want to really highlight these two bullet points here. And the reason I want to highlight these two bullet points is they have this key word that I keep talking about, rate. Both of them have rate, so remember, whenever you see the word rate, you need to be thinking d something over dt. And both of these questions are talking about the amount of water that is in the tank. This first bullet point is talking about water flowing into the tank, and this second bullet point is talking about water leaving the tank. They're talking about the amount of water that's in the tank. So therefore, it's talking about the volume of the water, which we're going to call V. So this is going to be dV over dt. Another clue that it's volume is if you look at the units here, they're both in meters cubed, and when you have this cube here, it's a clue that it's about volume. So it's dV over dt, where V is the volume of water in the tank, okay? So we need to form a differential equation using this. Now this is quite difficult because we have two bits of information here, with water going into the tank and water leaving the tank, okay? So let's draw a diagram in order to show what's going on here. So this first bullet point says that water is flowing into the tank at a rate of 0.48, and this second bullet point says that water is leaving the tank at a rate of 0.1 h, okay? So when we're making this differential equation for dV over dt, we need to consider both of these. So when we consider them, so this 0.48 is increasing the volume of water in the tank, so this is going to be positive, and this 0.1h is water leaving the tank, so it's, the water in the tank is decreasing, so therefore it's going to be negative. It's going to be minus 0.1h in the differential equation. So when we write this differential equation, we just need to combine and add together these two factors that are affecting dV over dt. So therefore dV over dt is going to be 0.48, so that's the positive increase, this 0.48, and then minus the 0.1h here, which is the water leaving the tank. So dV over dt is made up of two factors, the water flowing into the tank and the water leaving. Okay, so we have the differential equation dV over dt, but the issue is this is not what we want in the final answer. We want dH over dt. So how do we get this? Well, what we're going to have to do is we're going to have to construct another differential equation. And the way that we're going to do this is use this information here that the tank is a cuboid. So we can see this in the figure as well, that the tank is a cuboid. It's got base 8 and 3 and height 5. And what's also a cuboid is the volume of water that's inside the tank. It has base 8, base 3 and height h. So what we can do is we can figure out the volume of water that's in the tank, which is V, because we can figure out the volume of the cuboid here. So the volume is equal to 8 times 3 times h. This is the volume of a cuboid, these three sides added together, and therefore this will be that V is equal to 24h. And now what we can do is we can differentiate this in terms of h to get dV over dH, and then if you differentiate this 24h, this h just goes away. This is year 1 differentiation, is equal to 24. So now we have dV over dH is equal to 24. So in our final answer we want dH over dt. So if we consider this and we consider multiplying these two differential equations together, we're going to want dH in the numerator and dt in the denominator, and then we're going to want two other terms that are going to cancel out. And you can see that in both of these differential equations here we have this dV that we don't have in the final answer, dH over dt. So therefore, if we make dv these other two terms here, they'll cancel out and just leave us with dH over dt. Okay, so therefore we have this formula here. Now we have dv over dt, we figured this out before. This is this 0.48 minus 0.1h. However, the issue is we don't have this dH over dv, we have it the other way around. We have dv over dH. But as we talked about before, we can figure out dH over dv by doing 1 divided by dv over dH. So it's going to be 1 divided by 24, so it's going to be 1 over 24. So therefore, dH over dt is going to be dH over dv, which is 1 over 24, multiplied by dv over dt, which is this 0.48 minus 0.1h. I've converted these decimals into fractions, so we're not kind of multiplying decimals and fractions together. 0.48 is 12 over 25 and 0.1 is 1 over 10. If we expand this bracket here, so it's going to be 1 over 24 times 12 over 25, which is 1 over 50, and 1 over 24 times 1 over 10, which is 1 over 240. Now, if we look at the final answer, we want a 1200 in front of this dH over dt. So what we're going to do with this equation is we're going to multiply all the terms, we're going to multiply the whole equation by 1200. So therefore, if we do this, there'll be a 1200 in front of this dH over dt. 1 over 50 multiplied by 1200 is equal to 24, and 1 over 240 multiplied by 1200 is equal to 5. So therefore, we have this equation here, which is what's required. Okay, and then for part B, we're told that when the tap was opened, the depth of water in the tank was 2 meters, and therefore we need to show that this equation here is true, that H is equal to this. Okay, now this information up here, we're going to ignore this for now because it's not relevant at the moment, it comes later. We first need to get the equation into this format here, and the way that we're going to do that is we're going to solve this differential equation here. So remember the steps of solving a differential equation. Firstly, we need to get all the h terms onto one side of the equation and all of the t terms onto the other side. So what we're going to do first is divide both sides by 24 minus 5h, so it becomes 1200 over 24 minus 5h. dH over dt is equal to 1 to get all the h terms on this side, and then we get the t terms onto this side by moving the dt, so it becomes this here, this equation. Now, something I just want to mention quickly is I said that we need to get all the h terms onto one side of the equation, and I divided by 24 minus 5h to get this here. One thing you might have thought of is what we could do instead is this minus 5h, we could bring this onto this side by adding 5h to both sides. So on this side it goes away, and then on this side it becomes plus 5h. And when I look back on making these videos, it's probably showing something I should have mentioned before this. If you try this method, it won't work. And the reason is because when we look at this 1200 dH over dt here, this is in brackets. So this dH over dt is multiplying this 1200. And therefore the issue, if you try to bring this 5h onto this side, is you end up with this equation here, where you've got 5h plus, and then in brackets this 1200 dH over dt. And the issue with this is this dH over dt is only affecting the 1200. It's not actually affecting the 5h. This is kind of on its own. And then if you try and integrate this, it doesn't work. What we need to do is we need to divide both sides by 24 minus 5h. So therefore, when we do this, this will be incorporated into this bracket here when we divide, and it will be affected by this dH over dt. That's probably a bit of a complicated explanation. I just wanted to show you and tell you that if you try and do it by moving this minus 5h onto the other side, it won't work. We need to divide both sides by 24 minus 5h to get it into this format here. Okay, so now we need to do the second step for solving a differential equation. We need to integrate both sides. I've taken the 1200 out of this integral here to make it a bit simpler. So if we start with this side here, we need to integrate 1 over 24 minus 5h. Now this is of the form that we've seen already in this video. This is of the form 1 over x, but instead of the x being in the denominator, it's the 24 minus 5h. So therefore, when we integrate it, instead of being the natural log of the modulus of x, it's going to be the natural log of the modulus of 24 minus 5h. But remember, we also need to divide by the coefficient of h, which is this minus 5. So it's going to be minus 1 over 5. And then remember this 1200 at the front of the integral here. And then if we integrate this 1 dt on this side, we've seen this already in this video, this is year 1 integration, it's just t. And then remember the plus c on the end. And then we can simplify this because 1200 multiplied by minus 1 over 5 is minus 240. And then what we're going to do here, so if we look at the final format, we want it to be h is equal to this. And the problem is we have h inside a natural log at the moment. So we want to get rid of this natural log, okay? So what we're first going to do is we're going to divide both sides by minus 240. So we get that the natural log of this here is equal to minus t over 240, and then we've got the plus c on the end. We don't need to divide the c here by the minus 240 because this is a constant that we need to find, so it'll just kind of be incorporated into it, and we'll just find this at the end. And then what we're going to do is we're going to make both of these sides powers to base e. So remember, when you do this, when you do e to the power of a natural log, it cancels out and just leaves us with 24 minus 5h. We don't really need to worry about the modulus anymore. And then if we do it on this side, it's going to be e to the power of minus t over 240 plus c. Okay, so we have this equation here, and we have this plus c in the power. And we've talked about this already in this video, if you remember the laws of powers. When you have two things that are added together in a power, you can split them up into two different powers by multiplying the terms together, like this here. And then this e to the power of c, as c is a constant, e to the power of c will also be a constant. So if we say that a is equal to this e to the power of c, we can therefore write this as a e to the power of minus t over 240, which is a bit neater than this up here. So what we need to do here is we need to make h the subject. So what we're going to do, this 24, we're going to move this to the other side, so it becomes minus 24 on this side, and then we're going to divide both sides by minus 5 to make h the subject, so it becomes h is equal to, and then this minus 24 is going to become plus 24 over 5. We don't need to worry about dividing this a here by minus 5 because this is what we're trying to find, so we can kind of just absorb it in this constant here. And now we need to find a here, okay? And the way that we can do this is by using this information here, that when the tap was opened, the depth of water in the tank was 2 meters. So that means that h is equal to 2, and as it was when the tap was opened, this is when t is equal to 0, as this equation models the height of the water after the tap was opened. So therefore, when the tap was opened, t is equal to 0. This is initially what happened. So therefore, what we can do is sub these coordinates in. So we can sub in h is equal to 2 like this here, and then if we sub in t is equal to 0, this power here will become a 0, so it become e to the power of 0, which is 1, so this will just be a, and then we've got this plus 24 over 5 on this side, and then move this onto this side to get that a is equal to minus 14 over 5. So therefore we can write a complete equation here by subbing in this value of a. So we get that h is equal to 24 over 5 minus 14 over 5 e to the power of minus 1 over 240t, and this is in this format here. Okay, and then for part C, we're told that given that the tap remains open, we need to determine whether the tank will ever become full. Okay, so let's consider what this question is actually asking us. So we need to consider the diagram in part A, and the height of the tank is 5 meters. And as h is the height of the water in the tank, in order for the tank to become completely full, H will have to be equal to 5, because this would be where water completely takes up the tank. So what this question is actually asking us is, with this equation here, we need to figure out if H can be equal to 5 and if this tank can ever become completely full. Okay, so what we're going to do is we're going to sub in H is equal to 5 into this equation here and try and rearrange to find a value of t, so a time for when this occurs. Okay, so I've subbed in H is equal to 5 here, and let's rearrange in order to find a value of t. So let's move this 24 over 5 onto this side, so it becomes 1 over 5 on this side here, and then let's divide both sides by minus 14 over 5, so this side will become minus 1 over 14 is equal to e to the power of minus 1 over 250t. But here, this equation here, we have an issue. And the issue is, it doesn't actually really matter what this power is here. When you have e to the power of something, it's always bigger than or equal to 0. E to the power cannot be negative, okay? And the issue we've got here is we've got that minus 1 over 14 is equal to e to the power, which isn't possible. E to the power of minus 1 over 250t cannot be equal to minus 1 over 14. So therefore we have a flaw in this equation. There is no value of t for which h is equal to 5. So therefore the tank cannot be completely full. So therefore the answer is no. It is physically impossible, according to the model, for the tank to ever become full. Okay, so here's one final question for you to have a go at. I've split it into two again because it's a really long question. So it starts here and then goes down like this. So pause the video, have a go, and I'll go through the answers in about 5 seconds. Okay, so in this question we have this diagram here, and we're told that a tank in the shape of a cuboid is being filled with water, and we're told that the base of the tank measures 20 by 10 and the height of the tank is 5, and this is given to us in the figure. And we're told that at time t minutes after water started flowing into the tank, the height of the water was h meters, which again is given to us in the figure, and the volume of water in the tank was v meters cubed. Okay, and we're told that in this model the sides of the tank have negligible thickness, and we're told that the rate of v is inversely proportional to the square root of h, and we need to show that dh over dt is equal to lambda over root h, where lambda is a constant. Okay, so let's first focus on this bullet point here, where the rate of change of v is inversely proportional to the square root of h. So we have this key word here, rate, so it's going to be d something over dt, and we're told it's the rate of change of v, so therefore it's going to be dv over dt. And we're told that it's inversely proportional to the square root of h, so we have this proportional here, so it's proportional. So we're told it's inversely proportional, so it's going to be 1 over, and it's inversely proportional to the square root of h. So the square root of h here. So dv over dt is proportional to 1 over the square root of h. Remember what we talked about before? We can replace this proportional sign with an equal sign and a k constant. So therefore dv over dt is equal to k over root h, okay? And this k is a constant. Now we have dv over dt here. This is not what we want. We want dh over dt, so we need to find another differential equation. And we can do this because the volume of water in the tank is v meters cubed, and we can see that the volume of water in the tank is also a cuboid. It has base 20 and 10, and it has height h. So therefore we can say that v, which is the volume of water, is equal to 20 times 10 times h, okay? And then 20 times 10 is 200. So v, the volume of water, is equal to 200h, and then what we can do is we can differentiate this in terms of h. So it's dv over dh, and this is going to be equal to, when you differentiate in terms of h, this is just going to go away, and it's going to be equal to 200. Okay, so we have two differential equations here, this dv over dt and this dv over dh. Now we want dh over dt, okay? So when we multiply these differential equations together, we're going to want dh in the numerator and dt in the denominator, and we want the other two terms to cancel out. And similar to before, we can see that we have dv that is present in both of these differential equations that we don't want in the final answer. So this is what we're going to make these other terms so they cancel out, okay? So we have dv over dt, this is this k over root h. We don't have dh over dv, we have dv over dh. So therefore we can get dh over dv by doing 1 divided by dv over dh. So this is going to be 1 divided by 200, so it's going to be 1 over 200. So therefore dh over dt is going to be equal to dh over dv, so this is 1 over 200, multiplied by dv over dt, which is this k over root h, okay? Let's take this k out of this fraction here, so it's k over 200 multiplied by 1 over root h. And if we say that this lambda here is equal to this k over 200, because as k is a constant, k over 200 will also be a constant, we can say that this dh over dt is equal to, and then replace this here with lambda, so it's lambda over root h, and this is what they want in part A, where this lambda is a constant. Okay, and then for part B, we're told that initially the height of the water in the tank was 1.44 meters, and exactly 8 minutes after water started flowing into the tank, the height of the water was 3.24 meters. And we need to use this information to find an equation linking H and T in this format here, and we need to find what A and B are, okay? So what we essentially need to do is solve this differential equation here that we made in part A. This information here will come later when we're trying to find the constants, but first what we need to do is solve this differential equation. So remember the steps. So firstly we need to get all the h terms onto one side and all the t terms onto the other side. So firstly, if we multiply both sides by this root h, so this root h denominator will cancel out and leave us with root h dh over dt is equal to lambda, and then move this dt onto this side, so it becomes root h dh is equal to lambda dt. And then what we need to do is we need to integrate both sides. I have converted this root h into an h to the power of a half, if you remember your indices laws, because this is a bit easier to integrate. So if we start with this h to the power of a half, so this is just year one integration, so this power here goes up by 1 to 3 over 2, and then we divide by this 3 over 2. So it's 2 over 3 h to the power of 3 over 2, and then if we integrate this lambda dt, this lambda is just a constant, and we're integrating in terms of t, so therefore again this is just year one integration. This is going to be lambda t and then the plus c. So now what we need to do is find these two constants here, and we can do this by using these two bullet points that we give us here. So we're told that initially the height of the water in the tank was 1.44 meters, so that means that h is equal to 1.44, and we're told that this is initially at the start, so therefore t is equal to 0. And we're also told that exactly 8 minutes after water started flowing into the tank, the height of the water was 3.24 meters. So h is equal to 3.24, and we were told in part A that t is in minutes, so if it's 8 minutes after the water started flowing, t is going to be equal to 8. So what we need to do is sub these values of h and t into this equation in order to get out the values of lambda and c. So if we start with this here, we sub in h is equal to 1.44 and t is equal to 0, like this here. So this t here will be 0, so this term will cancel out and just leave us with this here equal to c. And then if you put this here into your calculator, you get that c is equal to 144 over 125. So therefore we've found the value of c, so we can sub this in, and now we can use this point here, h is equal to 3.24, t is equal to 8, so we can sub this into the equation like this here, and we can do some simplifying here. So if you put this here into a calculator, this 2 over 3, 3.24 to the power of 3 over 2 is equal to 486 over 125, and this 144 over 125, we can move this onto the other side, so we get the 8 lambda lambda is equal to 342 over 125, and then divide both sides by 8 to get that lambda is equal to 171 over 500. So we can also sub this in for lambda, and we get this equation here, that 2 over 3 h to the power of 3 over 2 is equal to this here. Now, if we look at what b is asking us, it doesn't want this 2 over 3 at the start of h as the coefficient. It just wants it on its own. So what we're going to do, we're going to divide both sides by 2 over 3. So on this side it cancels out, and then if you do the maths to these two fractions here, dividing them by 2 over 3, we get that it's 513 over 1000 t plus 216 over 25. So this here is the answer in this format. Okay, and then for part C, we need to find the time taken from when the water starts flowing into the tank for the tank to be completely full. Okay, so we have to look at this diagram here again, and we can see that the tank has a height of 5 meters. So therefore, for the tank to be completely full with water, this h here also needs to be equal to 5 for water to completely take up the tank. So what we need to do is we need to sub in h is equal to 5 into this equation here, and then rearrange in order to find t, and this will be the time taken for this to happen. So I've subbed in h is equal to 5 into this equation like this here, and then 5 to the power of 3 over 2 in decimals is 11.180, and then what we could do is this 216 over 125, we can move this onto the other side to get 9.452 is equal to 513 over 1000 t, and then divide both sides by 513 over 1000 using your calculator, and we get that t is equal to 18.4 minutes. So this is the amount of time it takes for h to be equal to 5. This is the amount of time it takes for the tank to be completely full with water.